Sorry for the interruption. Okay. Now let's continue. So therefore, in this form, this is the equation of motion for the new gauge field, or the new gauge field. And usually we will follow through by showing that these equations, actually there are 4 of them, because new could be 0, 1, 2, 3. So there are 4 equations. These 4 equations are just it's easy to see, to show that it is actually part of the Maxwell equation, part of the Maxwell equation. So part of the Maxwell equation give you the equation of motion, and it is I think I don't have the formula here. If you, oh, indeed I do. Okay, this is 3.141. Now, to continue, I don't have time to follow through all the derivation to analyze this equation of motion, but I can show you easy in a very short way that this partial mu f mu nu, if you choose a gauge, remember this is a gauge theory, so you are free to choose a gauge. And in this textbook, it shows you can choose a transformation so that this gauge condition we call Lorentz gauge is satisfied. Partial mu, A mu is equal to 0. We are allowed to choose a gauge so that this condition is satisfied. Then the equation of motion, partial mu f mu nu, here it is written down explicitly. You can see that it consists of 2 terms. This is the first term, this is the second term. However, in choosing this gauge, the second term actually vanished. Therefore, it only contains the first term. And the first term, partial mu, is just the Laplacian. So the equation of motion can be simplified in this gauge to Laplacian A nu equal to 0. So it looks exactly like the Klein-Gordon equation if you treat A0, A1, A2, A3 as separate scalar field. Of course, it's not true because the A nu is not a scalar field. However, it shows you that the solution of A nu actually look very much like Klein-Gordon equation. Okay, so in terms of 3.152, then it is easy to write down the solution, or we call plane wave solution of this equation of motion here, 3.153. The A mu is equal to exponential the ikx with k satisfying the dispersion relation k squared equal to 0. Okay, so this is so it showed you that this f mu nu, the Lagrangian, I write down here, actually satisfactorily or give you an equation of motion that satisfy all our requirements, including give you an equation of motion, and this equation of motion actually in physical sense corresponds to the Maxwell equation that photon field must satisfy. So after all these maneuvers, we can satisfy. We are convinced that this A mu is exactly this gauge field we just introduced is the field that describes photon. Okay, so if A describes photon, then this interaction actually gives you the interaction between photon and electron. So equation 8.8 is the starting point of quantum electrodynamics. Okay, which is one of the early triumphs of quantum field theory, which described the, again, interaction between electron and photon very satisfactorily and successfully. Okay, in I think during the 1940s to 1950s. Okay, so this gauge theory formulation of the QED is an example, an illustration of how powerful this idea of local symmetry is in field theory. Now, if let's extend, okay. So there are 3 points. I think. Let me try to say. They are. The first point is important. If you observe this A point, this Lagrangian, as I say this time, actually you cannot introduce a term that look like a mu here. Okay, this kind of term is not gauge invariant. You can check with yourself, because after the gauge transformation, A will get an additional term. This A will also get an additional term. So there are altogether 3 additional terms after transformation. They cannot cancel each other. Therefore, this kind of term is not invariant. And if you are familiar with quantum field theory of vector field, this kind of term is actually the mass term of the vector field. It's a mass term. Therefore, that's why we usually say the gauge field or gauge particle is always massless. It's always massless. It's always massless. It's due to the symmetry consideration. And therefore, if you want to use the gauge field to describe nature, then you somehow, because in nature, photon probably is the only massless particle. So if you want to use the gauge theory to describe nature, somehow you have to give mass in various ways to this gauge particle. So in quantum field, in the case of electroweak theory, then the way to give mass is the spontaneous symmetry breaking. That means the Lagrangian is gauge invariant. However, you need to introduce a gauge variant vacuum to break this invariance, to break this gauge invariance. Okay, so that's why this point 1 is very important. So let me emphasize again, gauge particle is always massless due to the symmetry consideration. Now, the topic today is to extend this gauge symmetry, abelian gauge symmetry, to non-abelian. By non-abelian, we usually consider SU2 as the first example. The part of reason is that the SU2 is actually the gauged SU2 actually happens in the nature because the standard model is gauge SU2. Secondly, what we learn from this part could easily extend to all the higher gauge symmetry, SU3, SU4, if there is SU4 in nature. Okay. Now, so that's why we usually start with SU2, because it's the simplest non-abelian gauge symmetry, and it could be easily extended to more complicated situation. Okay, so now let's consider SU2, and let's first consider the fermion field as a doublet. Of course, it doesn't need to be a doublet, but as you know, doublet is the fundamental representation of SU2. So that's why we start with this simplest representation, and we can derive almost all the property of the gauge field and representation. And again, it could be easily extendable to all the other more complicated representations. Now, so this doublet consists of 2 fields, Psi1 and Psi2. We collectively call it Psi. And under SU2 transformation, this Psi is multiplied by a 2×2 matrix. And this 2×2 matrix could be written in terms of the generator tau. tau are the usual Pauli matrices. You can check what they are from almost all the quantum mechanics textbook. Okay, and this psi is equal to exponential minus I tau dot theta over 2. The so-called tau dot theta means tau 1 dot theta 1, tau 2 dot theta 2, tau 1 dot theta 1 plus tau 2 dot theta 2 plus tau 3 dot theta 3. Okay, so that's what this notation means. We treat it almost as a three vector inner product. Okay, although tau 1, tau 2 are three matrices which do not transform. However, we can treat them almost like a three vector. Okay, and here in 8.18, there is a very useful commutation relation between all the tau, the generators. Okay, this 8.18 commutation relation are actually the fundamental property of the SU2. I have derived in the particle physics introduction course that this for every Lie algebra, for every Lie group, the Lie algebra, that means the generators and their commutation relation together determine the structure of the Lie group. So this is what we call the commutation relation. So commutation relation plus the generators determine SU2 explicitly. Okay. Now, so this is the SU2 transformation. And now, if I write the Lagrangian again as this Dirac form, however, remember now this psi is actually a doublet. So this is a column and this is a row. So remember this Lagrangian actually consists of two terms, not just one. However, in terms of matrix notation, you can write it simply in terms of 8.19. And it's your job, and very easily you could show that this Lagrangian is invariant under this global SU2. By global SU2, I mean this theta 1 and theta 2, theta 3. These three rotational angles are not depend on the space-time. Just like the alpha, when we talk about global U1 symmetry, alpha does not depend on the space-time. The same thing here for global SU2. I mean this theta I being space-time independent, and you can easily check after the global SU2 transformation, there will be a 2x2 matrix appearing here, and the unitary of the matrix will appear here, and U and U will multiply each other and cancel each other. Therefore, this Lagrangian is invariant. However, we can think of something now, so it's a global SU2 symmetry. But now we can extend this idea to local symmetry by simply allowing this theta 1, theta 2, theta 3 to depend on space and time. As I've written here, this theta now is a function of x. Just like in U1, alpha is a function of x. Then again, it's almost the same theory, the same story. When you do this local transformation, multiply by this psi by a u and this psi bar by a u prime, or u minus, sorry, not u prime, u minus 1, then there will be one extra term here. Okay, and you can see the similarity between this term and the one in the U1 symmetry. And therefore, we can easily see that this global symmetry this Lagrangian is not invariant under the local symmetry, local SU2 symmetry due to the appearance of this term. So our strategy is the same. We want to define a D so that this D will commute with the U here. Okay. Again, after the gauge transformation, psi will becomes U times psi. And we want to, from 8.22, it's obvious that this U does not commute. It cannot pass through the partial derivative. However, we want to introduce a covariant derivative so that U will pass or commute with this covariant derivative. And the prescription is almost like U1 symmetry, abelian gauge symmetry. Here, we introduce vector field, A mu. However, because this psi is a 2 by 2, it is a column. Therefore, when you multiply this column with two field components by something, usually you multiply it by a matrix. And the natural guess is that it is a 2 by 2 matrix, which consists of tau 1 and tau 2 and tau 3. So an easy guess is that it is tau dot A mu. Here, this A mu actually consists of three vector fields, as the textbook right here. So this A is not just one vector field, but three vector fields, AI mu. I could be 1 or 2 and 3. So here the textbook say 1 for each group generator. Okay, so since for SU2 we got 3 generator, therefore we got 3 vector gauge field. That means if you extend the consideration here to higher, more complicated D group, then for each generator you add 1 vector gauge field. For example, for SU3, it is famous that we know that the SU3 has 8 generator corresponding to 8 gluons. So that means in this case we have 8 gauge groups, 8 vector gauge fields. Okay, so it's a very easy correspondence you have to remember. Now I have to show you in terms of this way we can actually got what we want. That is the U will pass through D mu. So 8.24 is the requirement for us to define this covariant derivative. So it is not very hard to write down the transformation property of this A from 8.24. So the following 3 equations is to do this. So here, let me read through it very fast. So here, after transformation, this D is here, and the U becomes U. This psi becomes U times psi, and we wanted U to pass through the derivative. Therefore, it could pass through out to outside. So U times the covariant derivative. So you solve this equation, you get the relation between A prime and A. So therefore the derivative, this term is here, and here we have U times partial mu psi. U partial mu psi will cancel each other. Then the space-time derivative could also act on U, because remember this theta depends on the space-time. Therefore, we got this additional term here, and yeah, that's it. Okay, so this is the additional term that due to the space-time dependence of theta, and therefore you can see easily that this and you multiply the whole thing by So that means this the capital bracket, the bracket inside the bracket is equal to this, which is 2 by 2 matrix. Okay, and therefore I can multiply here by a u minus 1, which will cancel this. Okay, so multiply by u minus 1 will give you this term. Multiply by u minus 1 and then give you this term. Okay, so 8.26 is the transformation property of A mu. Okay, of A mu. And this term is what corresponds to the partial mu alpha in U1 symmetry. Okay, and therefore, yeah, that's it. Okay, so we usually continue to show you, and this 8.26 is the general property of the transformation of A mu of the vector field A. We usually continue to use a infinite transformation, infinitesimal transformation, which could be written as u equal to 1 minus tau dot theta when theta is very, very small. If you plug this formula into 8.26, then you can write down the transformation property of A when theta is very, very small. Okay, therefore you get 8.28. I don't want to follow through all the derivation. You can do it yourself at home and you get 8.28. So the transformation property when the transformation is small, when the transformation is infinitesimal, then is A prime equal to A minus partial mu theta I. So this part corresponds directly to the partial mu alpha that happens in U1. And then this is the first term, which is the transformation property of AI. Remember, this AI is a vector. So if it is a vector, it has a transformation property. It has to transform under SU2. So this term reflects this. This term reflects this. Okay, and it will appear. I remind you to observe that even though theta I is independent of space-time, this term will still appear for a global symmetry, for a global transformation. Okay, so that's why the author wrote that the second term, this, is clearly the transformation for a triplet transformation of SU2. Remember, again, AI is a triplet, A1, A2, A3. So it is a triplet. So even though the theta I is space-time independent, then it will still transform as a triplet in this way. Okay, that's almost it. So in this way, with the definition of 8.26 for a transformation property of A, and with 8.28 for a transformation property of infinitesimal, we succeeded in constructing a covariant derivative D, which allowed the U to pass through, which is the formal requirement here we have here. Okay, so if this is true, then it is just like in U1 symmetry, the Lagrangian. If you replace the partial mu with the capital D mu, then the Lagrangian is still gauge invariant. It's still gauge invariant. Okay, so so that's the part of the covariant derivative. So the next step is to write F mu nu. But now we don't have electromagnetism. Remember I told you that F mu nu is the electric field and magnetic field in U1 electromagnetism. However, now when we extend to generalize to non-abelian gauge theory, we don't have a guidebook as electric field and magnetic field. However, there is a mathematical tricks which, when we return to U1 symmetry, I can write F mu nu as the commutator of the covariant derivative. Okay, so here I have already returned to U1, and in U1 it's all mathematics. So if you calculate the commutator of two covariant derivative, here I write it as d nu minus d mu, and acting on, of course, it's a derivative, so it needs to act on a fermion field, and you can easily see, actually, because after the Lorentz transformation, after the U1 gauge transformation, the psi is multiplied by a phase. But as our requirement that the phase vector can pass through the derivative, the covariant derivative, so it can pass here and pass here, also pass here and pass here. So it's easy to see that after the transformation, this phase vector is, the whole thing is multiplied by a phase vector in the front, because it will pass through all the covariant derivatives. Okay, and therefore this d nu, if we write it as F mu nu, then F mu nu psi prime, and after transformation, this F mu nu is multiplied by a phase. Then you can easily see that then F mu nu after transformation is equal to itself before the transformation. Okay, so it's an easier way to derive that the F mu nu, the anti-symmetric tensor, is gauge invariant. So this gauge invariant tensor. And therefore, we are going to use the same calculation, the same mathematical tricks to derive F mu nu in non-abelian gauge theory. So in non-abelian gauge theory, because the requirement is the same, the requirement for this covariant derivative is the same. That is, the U, the transformation 2x2 matrix, can pass through this covariant derivative. Therefore, if I define the anti-symmetric tensor F mu nu as the commutator of two covariant derivative, as I say here, 8.29, I define F mu nu as the commutator of two covariant derivative, of course multiplied by the fermion itself. Remember, it is easy to guess that this F mu nu also needs to have three versions, because A has three versions. The vector fields have three versions, so it's obvious that this F mu nu anti-symmetric tensor also needs to consist of three versions. And it is now easy to derive here at 8.32. When you multiply after the transformation, then the U appearing here could pass through this and then pass through this. So it could pass to the front of the whole thing. That means this combination actually transforms exactly like the field psi itself. 8.32 is very, very important. Okay, and therefore, if this is true, then it is easy to derive the transformation property of F mu nu. So you just need to put 8.29 into 8.32. Then it is easy to see that after the transformation, f prime is equal to this, or easier, 8.33. When you multiply both sides by u, then it becomes this. So that means tau dot f prime actually transform like a triplet, or transform like a triplet. Okay, without as if the theta is not independent, is independent of space time. Okay, so as a global symmetry. So the point of 8.33 is that if you define your f this way, then f will transform as if the transformation is global. Therefore, we can write this form, trace tau dot f mu nu, tau dot f mu nu in this way. And then after transformation, we got a u here, we got a u minus here, we got a u here. Then this u minus and this u will cancel. After multiplication, you will cancel each other. Okay, and then there is a u here, and if you take trace, this u and u minus 1 will cancel each other. Okay, and it is customary to check that when you take trace, then this will become this. This will become this. Okay, and it recovered almost exactly the same form as the original f mu nu form of the Lagrangian of the U1 symmetry. Okay. Okay, so what remains to be done is to write down this f mu nu. Here I defined it as the commutator of covariant derivative. However, it could be written in more complete form in terms of the a. So 8.31 could be written in this way. Okay, so yeah, so I finished doing so we can put everything together into 8.35. Here 8.36 is the definition of AF antisymmetric tensor. 8.37 is the definition of covariant derivative. And with this transformation of fields, it is now, I have shown that the 8.35 is invariant under the local gauge symmetry, This textbook continue to show you if you can easily extend this mathematics to higher the algebra, okay, from 8.42. Okay, you can extend into higher algebra, higher Lie group. So it's a little bit hard to do it online. Okay, maybe next week when we can start to do the teaching in class, I can show you more clearly all the mathematics here. Probably we'll come back again to this derivation on the blackboard. Okay, so you can also try to do it yourself at home. Anyway, that's all I have to say today. It's a little bit not as organized as I would like. It's a little bit hard to have all these mathematics in online and without knowing how you react to the details. So maybe I will try next time again to finish the mathematics. But before that, let me say goodbye, and I'll see you next time. Probably we'll go to the classroom next time. Okay, see you.